Hello everyone. Welcome to this web presentation on the use of Flow 3D in the context of hydraulic, water resource and coastal engineering applications. Flow 3D is a general CFD package that is used in many other industries, aerospace, marine, metal casting, micro and biofluids in particular. And I would add that we have some major strengths with fully three-dimensional, complex, transient, free surface computations, all of which are of course key to accurate environmental flow modeling as well as to coastal engineering. So welcome and let's get going. Before we start, take note of my email if you don't already have it. I encourage you to write down questions, especially ones which relate specifically to your own applications and workflow. I'm definitely happy to respond to specifics or to expand on certain aspects of this presentation. I suggest you simply open a new email right now and leave it open for the course of the presentation. Jot down questions as you think of them as a list, then simply send me the email at the end of the presentation. No need to synthesize or organize your questions. Just send me the list and I will organize my responses around what you send me. No worries. Okay, so today's agenda. There's a lot of material, but I want to keep this under the 45 minutes mark, so I will move through the slides at a pretty fast clip, but don't worry, the presentation is being recorded and you will receive an email shortly giving you a link to download the PowerPoint presentation as well as the recorded webinar with the audio. So what I want to show you today is twofold. I want to demonstrate the broad range of applications that are tackled using Flow 3D, and I also want to show you the code's versatility, ease of use, and sheer computational power. In other words, what can be done and how it's done. There will also be a brief comment or two on Flow 3D MP, which is the high-performance parallel computing version of Flow 3D. Exactly the same interface, but allows you to tap into the power of multi-core clusters and high-performance computing. 3 parts to this webinar: a common setup in the form of a dam and topography model with moving sluice gates, and then some examples of applications and an overview of some physics modules. And finally, I will run through some World User Conference proceeding examples, some very interesting slides there, in particular some laboratory versus numerical experiments and built environments versus numerical environment studies, which collectively certainly can constitute some first-class validations, I think, for our code. Okay, so part 1. Before you even open Flow 3D, there are some preparations to be done. Flow 3D will not figure out the engineering fundamentals for you. You need to understand, from an engineer standpoint, the physics and scales and matter and that are relevant to your premise. You need to know what you are trying to model, and you also need to know what I call the lay of the land, so topography, upstream flow conditions, etc. The lay of the land is something, as I just said, you need to mention. This typically includes build structures, external forcing, flow conditions upstream, maybe the range of parameter space you might want to study, and so on. These fundamental quantities are yours to define as best you can, and again, I just want to make it clear that Flow 3D will not replace your engineering common sense and the homework you need to do before tackling a simulation. Okay, so this said, what do these building blocks look like? For the upcoming example that I'll show you in a minute, the data comes from the US Geological Survey National Database. In general, when you think about what resolution is required for your topography, it's good practice to put that in the context of your computational grid size. And since a foot scale grid size is not uncommon on downscale problems, at this point I would suggest you get the best topographical data you can, because computers have basically taken the lead for now, at least on these scales. So this is the topography we'll use today. Next we have the down geometry. I'll rotate this for you. Well, it's simply imported from your CAD package. It's very straightforward. Those sluice gates in red are imported as separate elements so that we can give them prescribed motions later if we want to do so. Again, the format to import into Flow3D is the STL format, but I don't know of any CAD package that does not export to STL, so everyone ought to be in good shape in that respect. But these are things that happen upstream, so to speak, from your simulation workflow before you open Flow3D. So finally, you put these elements together. We have a dam topography, and we have also added water levels upstream and downstream. And this is what I call the lay of the land. So if we move this around, this is the premise of our simulation. Okay. Okay, so we have our geometry. This gets imported into Flow3D, and the methodology then consists in following a series of steps. Namely, we need to decide which physics to turn on, create a mesh, define boundary and initial conditions, and choose which outputs we are interested in. Those are the fundamental steps. A few subtleties you can add into there. You can fine-tune the numerics, for instance, for a given kind of application, and it's good practice to run coarse grids and then fine grids and then finer grids to check on mesh dependency, things like that. But the fundamentals are quite straightforward and logical. So the Flow3D user interface looks like this, with different tabs which take you through the motions. There's a general tab which defines broad parameters of the simulation. Then we have a physics tabs, a fluids tabs, a meshing and geometry tab, and the outputs and numerics tab. Collectively, these basically both frame and detail the entire simulation. And I will open the actual Flow3D user interface in just a moment. Before that, I want to show you this view, which shows you what we call the favorized rendering of the initial conditions. This view basically shows you how well the geometry has been resolved by the computational mesh that you have defined, and gives you a feel as to whether your mesh is fine enough to resolve all the geometric features in play or not. So in Flow3D, objects are free to be placed anywhere within the mesh without any remeshing at all being required. Of course, you can nest finer meshes within coarser meshes in order to resolve finer details. The basic premise, though, is that what we call free gridding, which is a very, very powerful feature of Flow3D. So if you change your geometry, you do not need to remesh anything at all. Things just float in space. Okay, so let's see. This is the Flow3D graphical user interface. We have the topography, which I just showed you, and if I zoom in, We have the dam and the sluice gates, and we have, in this case, a small mesh which is surrounding the immediate vicinity of the dam. These are the edges of the mesh. And we have boundary conditions on all 6 sides of the mesh. So when these are the tabs I was referring to just a minute ago. The general tab, which gives you the sort of general kind of simulation that you want to carry out. So you could have a free surface or sharp interface. So this is the interface tracking, or you could have no sharp interface for confined internal flows. You can have 1 or 2 fluids, your units, the number of processes you would like to use, and the finish time, in this case 90 seconds. The meshing and geometry tab, this is where you would import your STL files, lay them out in space, and then on the left here you have basically your geometry window with all your components. In this case we have 6 components. Then on the right here we have the mesh operations. So if I look at the mesh, we can see in this case I have a fairly fine mesh, fine enough to resolve all of the geometry and to give us some good results. And you have other windows, so the initial conditions, where you can define basically what's happening at time t equals 0. And then we have boundary conditions. So if I open, for instance, these boundary conditions, we have different boundary types. So we have symmetry, all classical boundaries, wall, continuative, periodic, specified pressure, stagnation pressure optionally, velocity, grid overlay when we want to use data from another simulation as a boundary condition. This happens quite often in larger scale problems or coastal modeling problems when we might use the input from, or the output rather, from a maybe a geophysical model, larger scale model. Wave boundary conditions, all sorts of different waves we can, models we can choose from, and we can also choose various wave spectrums for ocean wave spectra. Okay, the physics tabs is probably the most interesting one. All sorts of physics, most of them highly relevant to hydraulic problems, not all of them though. Some are also specialized for different applications, in particular metal casting and molten metal flow, heat transfer, that sort of stuff. So I'll start with the top left, air entrainment. Useful for ecosystem, ecological studies, also bulking studies in ducts. Very efficient, works very well. Bubble and phase change, usually for smaller scale problems, cavitation. Core gas is a module that is really for metal casting, but any of these physics modules, you basically just click on, off, you just turn them on and off, and that's how you activate different physics that you want to capture in your simulation. So I'll leave this on. Defect tracking is for metal casting. Density evaluation, very important for coastal circulation, obviously, also for some reservoir problems, baroclinic flows, thermally or saline or thermal stratified flows, coastal circulation. This is an important one. Dissolving objects, salts, that sort of stuff. Drift flux, sediment transport, very important. Fluid sources, also very important. Granular flow, useful for things like avalanches or landslides. I will open this one, the gravity and non-inertial reference frame. So this one's basically always turned on if gravity is in play. So in SI units, it's minus 9.81. And we also can activate non-inertial reference frames. And for geophysical flows, we can also include the Coriolis acceleration in our computations. Heat transfer is sometimes relevant. Lost foam is a metal casting one. Moisture can be very useful. Moving and simple deforming objects. We call this a GMO model. Very, very, very useful and powerful module in Flow3D. Objects float in space, but they also move freely around and can be fully coupled with the fluid. So they can push on the fluid and the fluid can push on them. And we capture the resulting motions fully and accurately. We can also activate collision in the case of two solids colliding. Okay, so this is an important one. Particles, very, very useful for looking, visualizing what's going on, also tracking residence times, that sort of stuff. Porous media, also very, very useful in many applications, hydraulic applications, scalars, including filters, by the way. Scalars, also good for contaminants or specialized quantities. Sediment scour, also a big one for bridge piers. Shallow water is a model which is, instead of capturing the full 3D, we use the vertically integrated Navier-Stokes equations. So this basically allows you to have something close to 3D results, but you're using a 2D mesh. So it's a huge savings in computational expense in terms of cell numbers. Solidification is for metal casting. Surface tension, important for capillary waves, obviously, bubbles, that sort of stuff. Thermal dicycling is a metal casting one, and then viscosity and turbulence, ubiquitous, of course, in environmental flows. So viscous flow, we have some specialized viscous flows as well, and then a bunch of pretty advanced turbulence models. The two useful ones really are the K epsilon model and the renormalized group model. I usually just stick with the RNG model because it works pretty well in many cases, not all cases, but many cases. And coming up next spring will be K omega turbulence model. Okay, so we have our physics, our meshing. The fluids is fairly trivial. We have, the density of water, viscosity. These are just basically properties of the fluid, or sometimes two fluids if we are doing a multi-fluid problem. Everything is a lot of detail, but it's all basically properties. Next, we need to choose what it is we want to get out of the simulation. So all sorts of quantities that we can actually output. I mean, there's all the usual stuff, but some additional things. We have filling time, strain rates, fluid residence time, hydraulic data, of course, will be of interest to most of you. Vorticity, shear stress sometimes on elements. Trace, I'll go through these quickly. Fluid fraction, fluid temperature, velocities, vorticity, hydraulic data, internal energy, particle information, pressure, hydraulic head, traces, kinetic dissipation and energy, and entrained air. And depending on the physics you turned on, more or fewer outputs will be available. But then, of course, the more output you choose, the larger the output files. So usually you will simply choose what you need for your specific purposes. Numerics. Most of this is actually the defaults are very, very efficient and robust. So in practice, you will actually never touch much of this. The choice you'll do most often is to choose the order of accuracy on the advection. And occasionally the tracking algorithm for the interface. Okay, so model setup is quite simple, really. You have your general parameters, your physics, your fluids, your meshing, your output, and your numerics. And at that point, you would run the simulation. And while the simulation is running, you can monitor a bunch of different metrics, mean kinetic energy, which is a good one to know when you've reached steady state, for instance. But quite a few things you can look at here which tell you how the simulation is going. Okay, so at this point I will go back to the webinar, or rather to the PowerPoint presentation. Okay, this is for reminder, and this is for the sake of completeness for the standalone PowerPoint presentation. So I've just been through this, so I'll skip over this slide. Okay, so recap. It's ease of use, I guess, is the take-home message. STL import of topography, bathymetry, and solid components. Free meshing allows users to seamlessly modify configurations at will. There's no remeshing involved. Objects are embedded within the mesh, and the physics modules and higher order numerics are just basically turned on and off as desired. I think those are the key elements that make Flow3D extremely versatile and very efficient time-wise as a modeling and simulation tool. So I've been through this, but again, for the sake of the presentation's completeness, the output of the simulation for reference as well. So what do we actually get out of this? Here's an example then of the outcome of the simulation. In this case, the inflow volume flow rate upstream is actually very high. So this is a much more energetic flow than you would normally see, but for the sake of visualizing what's going on, it's quite useful. There's also, you'll see in a second, an example of the general moving objects module with the sluice gates being given a prescribed motion in orange on this video. Okay, the same simulation with the topography turned off, so you can see the fluid slosh around the basins. And again, the gates moving up. Okay, and this is a similar simulation. In this case, the sluice gates remain closed and the water discharged through the spillway. This one included air entrainment and particle tracking, which is why I put it here too. So you can see the flow's three-dimensional behavior in great detail. So not just the free surface, but what's going on underneath. The color here shows the volume fraction of entrained air. In short, setting up a simulation is straightforward once you have the structural and topological elements in place. And it's really engineering common sense more than anything else that will ensure that you will get good results out of your simulation. There's some best practice rules to follow, which of course we train our users with, and thereafter you're in good shape. Okay, so in part 2 I have some examples of different applications and physics modules. So let's get right into it. These next two slides are important, at least for reference. I have compiled a list of applications relevant to water engineering for which Flow3D users use our code. No pictures, but a lot of information, and this list might give you something to think about. The first major category is open channel flow studies. Dams, intakes, particular transport, scour, catastrophic failure, sloshing, and so on. There isn't much actually that cannot be modeled by Flow3D when it comes to transient full 3D open channel hydraulics. We basically capture the full set of physics and do it in a way that's robust, accurate, and I should add, very fast. Okay, also worth mentioning the hydraulic zone of influence, which is becoming an important study in light of the recent EPA directives for power plants, cooling, intake channels, that sort of stuff. We handle that very, very well. Next two areas that are commonly used with Flow3D, municipal flows. We have sewers, complex flood studies, tanks, mixing, pumps, hydraulic shocks, cavitation, all of those we handle well, settling tanks too. And then for coastal modeling, tsunami surge detail simulations, contaminant transports, buoyancy-driven flows, baroclinic flows, wave surge, hydrodynamic forcing on structures, wave energy dissipation, and conversely wave energy harvesting structures. A lot of work going on in that field. Coastal protection structures, also a lot of work being done by our colleagues in Japan. Explicit wave forcing, shallow water equation modeling, of course, and then what we call hybrid shallow water full 3D modeling, which I'll get back to in a minute, but basically allows you to nest full 3D meshes, fine meshes around the detail of structures, but you can nest that within much bigger scale shallow water meshes. So it's a mix of integrated 2D meshes with full detail 3D meshes. That's a very powerful feature of Flow3D. Okay, so some examples. First, at the core of Flow3D is the volume of fluid method, and we'll see how we capture the complexity of these flows. This is an example of a discharge flow, and you can see how the volume of fluid method does a pretty good job at capturing the full dynamics of these flows. Quick historical note. Flow Science founder Dr. Hurt invented the volume of fluid method a while back, and in fact this method has been improved and optimized here in-house at Flow Science ever since, which is why it is so efficient at this point in time. It's actually called TrueVoF these days. The result, though, is a very cost-effective, fast and powerful sharp interface and free surface modeler. So a few examples of the general moving object module that we have. It can be used in all sorts of situations. Anything that moves and interacts with water is well resolved with this module. Interesting here for residence times. Ship launch. Ship geometries can be very accurately modeled. You can put the radii of gyration, mass, everything, geometry. Works very well for ships. And then even in this low resolution simulation, you can still see the hydraulic jump forming downstream behind the tainter gate. Hydraulic screw. With a real life example here. And this is a simulation of a very, very viscous flow being stirred, mixed. Okay, so the general moving object is absolutely one of the most powerful features in Flow3D, and it works seamlessly within the free gridding meshing, so it's all around just a really, really powerful tool. Some coastal engineering. Breakwater structures, common problem in coastal engineering, and if you look behind those tetrapods you can clearly see how the waves have been damped, and in terms of outputs, of course, you can measure all sorts of things before and after, turbulent kinetic energy and so on and so on. But you see how the three-dimensionality of the simulation works very well to get an accurate idea of what's happening behind the tetrapod. Another application of the general moving object, this is a landslide into a reservoir. These kinds of simulation have been actually done in for completely real industrial applications. Oops, I should go backwards. So what we'll see here is the landslide element here in green, which is going to slide into the basin, and we are interested in knowing something about the wave propagation that ensues following this event. So a bit disorganized at first, and then you can see a wavefront moving upstream here, wavefront propagation. At that point, we have close to 10 meters in wave height, so pretty significant. There's a detailed view. Scour and deposition is another module we have. So this is the bed. We can't see the water. It's the bed around a pier. And what we can see is this is a symmetric simulation. So this is the packed sediment height around the half symmetry. This model, there's a paper in the, I will be sending you a link, but there's a paper from NC State which shows some very nice agreements between actual measurements and numerical measurements. Nice paper which I will share with you shortly. Sloshing is maybe more important for, it's actually very important for aerospace applications, but it's also used in marine applications, tanks. but it can also be used in conjunction with the non-inertial reference frame, and in this example I took the time series from the LA Dam 1994 earthquake. So we have XYZ acceleration components, which are seismic measurements of accelerations at the foot of the dam in 94. This is just one direction, but what you can see is 1, 2, 3, 4, 5, 6 peaks, which can be modeled very easily as non-inertial in a non-inertial time frame setup. So this is an idealized tank. I think the length scale is about 400 meters. Yep. And we see that the earthquake generated that's 18 feet wave height, and the time is at 160 seconds, so way after the initial impulse. If I go back, the initial impulse lasted 20 seconds, and the response was modeled up to 400 seconds or so, with still very consequential waves. It's easy, of course, to just add topography, and then the topography, the modes are more complex, of course, in this case, but we're still getting, this case, 4 feet wave sloshing around the basin. There you go. Now this example is a drop shaft structure for municipal flow. So what we have is on the top right here we have sewer water coming in, and then as it falls down it entrains a lot of air, and some of those bubbles will float up to the surface through this exit ducts, and this duct connects to the central network of the sewer system. This was modeled, I think, for the city of LA. And the issue is when you have too much air entrained in the water, of course you get bulking, which in effect reduces the duct capacity. So sewer drop, inflow, and then dark blue is all liquid, and colors mean that there's more air entrained. Okay, so the fluid falls down, you can see the air entrainment, and then some of the air goes up the duct, the exit duct, and some of it goes into the main system, and that's what we're interested in knowing. Okay, so air entrainment, turbulence, bulking, all of this in the context of municipal flow. We've seen this one already, but it illustrates the particles and, again, air entrainment. You can see the recirculation underwater upstream of the jet impinging into the body of water there downstream. And you can also see whether or not the jet is actually impinging on the bottom surface. That's not always the case, but in this case it is. Okay. This is an example of the hybrid 3D mesh I was talking to you about earlier on. So we have a high resolution mesh here and a low resolution, well, the 2D shallow water equation mesh down here. So what we see is water coming out of a spillway and then propagating down the basin. So this part is a 2D shallow water mesh, and the detail at the top, which you can't see just yet, but this is the detail part of the same simulation. This is the detail that you capture with the full 3D local mesh, which is seamlessly integrated into the shallow water mesh. So for reference, these are the physics that we've already talked about. I won't read this again. Brief parenthesis on MP, Flow3D MP. This link, very interesting, high performance computing. What's great about MP is that the interface is exactly the same as in Flow3D, but you're tapping into greater computational resources, and there will be a webinar focused exclusively on this at the end of August. You can register here. And also some benchmark data for all sorts of applications, one of them being hydraulic dam setup, and you can see the upscaling as you increase the number of cores. It scales up very nicely. But in fact, most of us do not have access to these clusters. So my workstation, I have a $2,000 basically Intel i7 6-processor machine, and when I run this model with 1.6 million cells, the simulation, 60-second simulation, is done in 1 hour and 32 minutes. So that's pretty good. If I'm more ambitious and want 11 million cells for something pretty accurate, 1 meter cells around the dam, the simulation time then is 30 hours, which is still pretty good considering the scale and the detail of the simulation. So recap: broad spectrum of physics, ease of use, and power, speed, and scalability. That's, I think, the take-home message. Real quick now, and I'm not really going to go in any detail here, I want to basically encourage you to go to this public folder and download conference proceedings. World user conference proceedings are a really nice way to see what other people use our code for. First example is AECOM, Jean-François Mercier, who did a couple of really nice studies a couple of years ago. This was a Fishway passage optimization, and really just to show you that the numerical versus built environment connection. Also the ease to run the parameter space with different volume flow rates, and some comparison between predicted numerical modeling results in red and the actual measurements in the built environment, full scale. Pretty good. So the conclusions are that, in this case, that the model works very, very well, and the so you can also run these big simulations, really big simulations, now in a matter of days, basically, just on a desktop computer. Just again, the connection between the built environment and the numerical environment. And so I encourage you to basically download this presentation and look at the detail. It's very interesting. URS did a few other companies have done this too, but URS have basically systematically compared lab models with numerical models since 2007, and at this point they have well over 20 projects actually comparing numerical and lab model. Very interesting papers. What you want to be looking at here is the red dots versus the blue measurements, also very good. And I would just note that I think this actually has to do with the boundary conditions downstream not being placed far enough downstream, which is the discrepancy here. Again, built environments, numerical environments, lab environments, numerical environments. At this point, Flow3D has been validated, even for complex situations, has been validated over dozens and dozens of studies. Worley-Parsons is also one of those companies that has done extensive testing and between the built environments, the lab environment, and the numerical environments. And again, I refer you to the conference proceedings, which you can download at this link, and I'll be emailing you all this information very shortly. Okay, so reminder, I hope you jotted down your questions, Don't hesitate to email me. We've actually already seen this video, but I'll play it again just because of the next slide. But yes, write down your questions, email me any questions you have, and I will respond as best I can. So this is the detail, as we've already seen, of a breakwater idealized structure, and what our friends in Italy have done, I think in the European User Conference, something similar in a real case study. And again, you can look at this, download this paper in the conference proceedings. The output that's really useful, of course, is the hydraulic action on the selected blocks here. This is a sort of direct output from Flow3D. Okay, review, wide range of physics, ease of use, highly optimized numerics, and seamlessly scalable to clusters and high-performance computing applications. So all in all, a very strong all-in-one package for advanced hydraulic, coastal, and water engineering applications. Any questions, email me, and thank you for everyone for tuning in and listening.